The universe we inhabit might just be one slice of an infinitely larger cosmic pie, where alternate realities exist side by side, shimmering just beyond our reach. The idea of traveling to a parallel universe isn't pure science fiction. It's something physicists debate with serious curiosity, rooted in cutting-edge theories like the multiverse hypothesis and quantum mechanics. Imagine discovering a version of yourself living a different life, or solving mysteries of existence that have baffled humanity for centuries. Today, we're diving into the bold question: can we tear through the fabric of our reality and step into these hidden worlds? Stay tuned, because what if the key to unlocking vast new horizons is hiding just behind the veil of what we think is possible? The concept of parallel universes in science fiction and theory. The idea of parallel universes first gained scientific traction through the multiverse hypothesis, which emerges from extensions of quantum mechanics and cosmology. In quantum theory, the many worlds interpretation suggests that every quantum event spawns new branches of reality, each representing different possible outcomes. For example, if a particle has a chance to spin either up or down, then in this framework, both outcomes occur, but in separate, non-interacting branches of the universe. This concept fundamentally challenges classical notions of determinism and offers a mind-bending perspective. Every decision, every fluctuation, possibly creates a new universe. Cosmology adds another layer to the concept. During the inflationary epoch, an extremely rapid expansion of the universe after the Big Bang, it's theorized that different regions could have budded off into separate bubble universes. In this scenario, our universe is just one bubble among an infinite mixture, each with potentially different physical constants, laws, or structures. This idea leads to a startling possibility that the universe's fine-tuning for life might be explained by a vast, possibly infinite, landscape of universes where only some are hospitable enough for intelligent observers. While directly observing these other bubbles remains out of reach, their existence is a serious scientific consideration that blurs the lines between physics and metaphysics. In science fiction, these theories serve as fertile ground for storytelling and speculative simulation. Writers have imagined entire worlds that exist side by side, accessible through advanced technology such as portals, wormholes, or quantum devices. These tales often explore the implications of traveling between universes, encountering alternate versions of oneself, discovering worlds with different histories, or even facing the existential challenge of whether such journeys could be safe or even possible at all. While current technology doesn't allow for literal travel to these other realms, the narratives keep the curiosity alive, fueling both popular imagination and scientific inquiry. Scientists continue to debate whether the multiverse concept is a testable hypothesis or remains a philosophical extension of modern physics. Experiments targeting cosmic microwave background radiation, for instance, suggest subtle anomalies that might indicate interactions with other bubble universes. Still, the idea that someone could physically step into a parallel universe, and that these universes exist as tangible realities, is far from realization. That said, as theories develop and observational techniques improve, the boundary between science fiction and science fact grows increasingly blurred, inviting us to constantly reconsider what is conceivable. Historical roots of multiverse ideas. The concept of multiple realities or parallel universes isn't a modern invention rooted solely in science fiction. It has deep, often philosophical origins that stretch back through centuries of human thought. Early metaphysical debates among ancient philosophers toyed with ideas that the universe might contain realms beyond physical perception. Plato pondered the existence of perfect forms or ideas that transcend our material world, hinting at a layered reality that could parallel the sensations we experience openly. These notions, although abstract, planted seeds that would later influence scientific curiosity and speculation. During the Enlightenment, thinkers began approaching reality through the lens of rationalism and emerging scientific method, which gradually opened avenues for considering worlds beyond our own. While early scientific paradigms still grounded their models in observable phenomena, some philosophers and astronomers entertained the idea that the universe might be part of an infinite multiverse. An example can be found in the work of Bernard of Fontenelle, who speculated on the possibility of countless worlds existing simultaneously, each with their own planets and inhabitants. His ideas pushed the boundary between poetic imagination and proto-scientific conjecture, blending the poetic with the rational in a way that challenged the nascent scientific culture to think bigger. The advent of quantum mechanics in the 20th century revolutionized notions of reality, offering some of the clearest scientific footholds for multiverse theories. The famous many-worlds interpretation, rooted in Hugh Everett's work, proposes that every quantum event spawns a branching universe, a kind of cosmic decision tree in which every possible outcome happens somewhere. This idea echoes old philosophical notions, but is now supported by mathematical formulations that suggest these parallel worlds could be just as real as our own. While still speculative and unobservable with current technology, the multiverse concept gained traction because of its elegance in solving quantum paradoxes, such as Schrödinger's cat or quantum entanglement. Throughout history, the philosophical underpinnings and scientific theories that entertain the existence of parallel universes reflect a persistent human desire to understand whether our universe is unique or merely one among countless others. From the metaphysical debates of ancient Greece to the complex frameworks of modern physics, the idea that multiple realities could exist has continuously challenged and expanded our perception of what reality might encompass. Despite the gap between hypothesis and empirical proof, these early roots remain vital threads in the ongoing tapestry of scientific and philosophical exploration about the broader cosmos. Quantum mechanics and the many-worlds interpretation. In the realm of quantum mechanics, the notion that particles don't have definite states until observed radically shifts our classical understanding of reality. Instead of a single, fixed universe, quantum theory suggests that multiple possibilities coexist simultaneously at the subatomic level. The many-worlds interpretation, MWI, capitalizes on this idea, proposing that every quantum event results in a branching of the universe into separate, non-communicating outcomes. When a measurement occurs, instead of collapsing into a single result, the universe splits, creating parallel branches where each possible outcome is realized. This concept reframes the question of can we travel to whether these parallel branches are accessible or merely theoretical constructs. The implications of the MWI stretch into profound philosophical territories. If every possible event occurs in some branch of the universe, then an infinite multitude of worlds exists, each one representing alternative histories and futures. These worlds are often visualized as a vast, ever-expanding tree where every decision, every quantum fluctuation spawns new branches. For instance, consider the simple act of flipping a coin. In one universe, it lands heads, in 10 others tails. Scaling this up, the totality of reality becomes an unimaginably complex constellation of parallel universes, each a different but equally valid manifestation of reality. While these branches are conceptually distinct, they are entangled with each other in the quantum fabric, subtly intertwined at a fundamental level, though no current technology can access or travel between them. The question of whether humans could ever traverse these alternate realities enters the territory of speculation intertwined with cutting-edge physics. Under the current scientific paradigm, there is no known mechanism for moving physically between these branches, no wormhole or quantum tunnel that would allow a conscious traveler to jump from one world to another. The issues are not purely technological, but foundational. Quantum decoherence ensures that once a branch diverges, the worlds evolve separately, making such travel appear impossible within the framework of known laws. Still, some theorists entertain the idea of quantum gateways, or utilize the principles of entanglement and superposition as conceptual tools to tease out the possibility, but these remain firmly in the realm of philosophy rather than empirical science. Ultimately, the many-worlds interpretation offers a captivating lens through which to contemplate the fabric of reality. It transforms the universe from a singular, deterministic entity into a vast landscape of countless parallel worlds, each diverging at every quantum decision point. While current understanding and technology do not permit travel across these alternate universes, the very notion challenges us to reconsider the boundaries of what is physically possible. It invites a perspective where the universe's magnificence lies not solely in what we observe, but also in the infinite, hidden tapestries of realities that coexist in the quantum realm shadow. String theory and extra dimensions. In the realm of modern physics, string theory stands out as one of the most ambitious attempts to understand the universe at a fundamental level. Its primary proposition is that all particles we observe, electrons, quarks, photons, are actually tiny vibrating strings. The specific vibrational pattern determines each particle's properties, such as mass and charge. However, one of the most intriguing aspects of string theory is its reliance on the existence of additional dimensions beyond the familiar three spatial dimensions and one time dimension. While our everyday experience confines us to length, width, height, and time, string theory mathematically requires at least 10 or 11 dimensions for its equations to hold consistently. These extra dimensions are thought to be compactified or curled up on scales so tiny that they elude direct detection, often shaped like complex Calabi-Yau manifolds. These curled-up dimensions aren't just a mathematical curiosity. Many physicists believe they could hold the key to merging quantum mechanics and general relativity, two of the most successful but incompatible theories in physics. If these extra dimensions do exist, they might contain pathways or bridges between different regions of space, or even different universes altogether. The concept of a multiverse becomes more plausible when considering how these compactified dimensions could serve as hidden gateways, offering a theoretical playground for parallel universes. Some interpretations suggest that particles traveling through these extra dimensions could manifest as different particles or forces in our familiar universe. And this opens the door to the possibility that other universes, with their own unique physical laws, could exist within this higher dimensional space. The challenge lies in the fact that extra dimensions are, by their nature, unfathomably small. Current technology cannot directly observe them, and their effects are usually only noticeable indirectly, such as through minute deviations in gravitational behavior at very small scales or through high-energy particle collisions. Experiments using particle accelerators, like the Large Hadron Collider, have sought signals of extra dimensions, such as missing energy patterns or the production of microscopic black holes, that might indicate their presence. So far, no definitive evidence has emerged, leaving the question open but tantalizing. The idea that one could travel to or access these extra dimensions, let alone cross into parallel universes, remains firmly in the speculative domain. Some theoretical constructs hint at mechanisms like wormholes or higher dimensional brains that could, in principle, connect different regions of space or different universes within a multidimensional framework. However, these ideas face enormous scientific and technological hurdles. Stabilizing such structures, understanding the physics at these scales, and figuring out whether or not they could be manipulated for travel. Although our understanding is far from making this a practical possibility, contemplating the existence and properties of extra dimensions fuels both scientific curiosity and imaginative speculation about the nature of reality itself. Cosmic inflation and bubble universes. The concept of traveling to a parallel universe often begins with the theory of cosmic inflation, a rapid expansion of space that occurred fractions of a second after the Big Bang. This exponential stretching smoothed out the universe we experience, but it also set the stage for a far more complex multiverse. According to inflationary models, the universe didn't just expand uniformly. Different regions could have experienced varying rates or even different endpoints, leading to the formation of isolated bubble universes. Each bubble might have its own physical laws or constants, creating a patchwork cosmos where what we see as our universe is just one among countless others. These bubble universes, separated by regions of space that no light or matter can traverse, could potentially host entirely different realities. Delving deeper, the idea of a multiverse arising from eternal inflation, an extension of the inflationary model, posits that the process of bubble formation is ongoing. As some regions stop inflating and form stable universes, others continue to inflate, spawning new bubbles in an unending cosmic process. This leads to an infinite or near-infinite multiverse, where each bubble universe emerges with its own unique set of physical parameters. Theoretically, some bubbles could be so radically different that they defy our understanding of physics entirely, making the notion of travel between them a challenge that borders on the speculative. The boundaries between these universes are theorized to be insurmountable because of the exponential expansion, but quantum tunneling or other conjectural mechanisms occasionally come into discussion as potential methods for bridging this cosmic divide. In terms of actual travel, current scientific understanding renders crossing into another bubble universe an extraordinary challenge, if it's possible at all. The scale of cosmic inflation stretches the fabric of space-time in a manner that prevents any known mechanism from moving matter between bubble universes without destroying it or fundamentally altering the laws of physics involved. Even concepts like wormholes, which are sometimes discussed as theoretical shortcuts through space-time, would require conditions and energies far beyond what humanity can achieve. Some physicists entertain the idea that quantum fluctuations might create tiny islands of universes within a larger inflationary landscape, but whether these can be accessed or traversed remains purely speculative. Essentially, the multiverse hypotheses open doors for philosophical and theoretical exploration, but still remain firmly outside the realm of practical interuniversal travel, at least with current or foreseeable physics. The role of black holes in potential universe connectivity. Black holes, with their intense gravitational pull and mysterious event horizons, have long fascinated scientists and theorists as potential portals or bridges between different parts of our universe, or perhaps entirely separate universes. According to some theoretical models rooted in general relativity and quantum physics, black holes might not be the ultimate cosmic dead ends that they seem. Instead, they could serve as gateways to other regions of space-time or even parallel realities if such exist. The idea hinges on the notion that black holes may contain wormholes, hypothetical tunnels that connect distant points in space and time, or possibly different universes altogether. Within the framework of Einstein's equations, wormholes are solutions that describe shortcuts through space-time. Though most of these solutions appear unstable or require exotic matter with negative energy density to stay open. Intriguingly, black holes could morph into such wormholes if certain conditions are met. For instance, the concept of a curved black hole, which rotates, introduces the possibility of a ring-shaped singularity and a corresponding passageway that could, in theory, connect to another universe or distant parts of our own. Some physicists speculate these structures might be ephemeral, collapsing before they could offer any practical means of travel, yet the mathematical possibility persists. Experimental verification remains elusive, of course. No direct observation of a wormhole or a black hole acting as a connection point to another universe has been made. Still, recent advances in gravitational wave astronomy have provided insights into black hole mergers, confirming the existence of these entities and their extreme properties. Such data helps refine models that include the possibility of interuniversal links. The reality might be far more complex than traversable doorways. Black holes could be more like cosmic recycling centers, where matter and information are preserved in ways scientists are only beginning to understand. The role of black holes in potential universe connectivity is thus a tantalizing mix of concrete physics and speculative imagination. While the notion of slipping through a black hole to another universe remains speculative from a scientific standpoint, it pushes the boundaries of what we consider possible in cosmology. Whether future discoveries will validate these ideas or dismiss them outright, the central notion, that black holes might be more than destructive voids remains compelling. Exploring their true nature could unlock secrets not only about the universe we observe, but also about the existence of alternate realities that might be woven into the fabric of the multiverse. Wormholes as bridges between universes. Wormholes, often depicted in science fiction as cosmic shortcuts, are intriguing solutions within the framework of Einstein's general relativity. They are theoretical passages through space-time that, if they exist, could potentially connect distant regions of our universe or even different universes altogether. The idea is rooted in the mathematics of solutions to Einstein's field equations, such as the Einstein-Rosen bridge, which describes a tunnel-like structure connecting two separate points in space-time. While such objects are mathematically plausible, their physical realization remains speculative, primarily because maintaining a stable wormhole would require exotic matter with negative energy density, something not yet observed or confirmed to exist. The notion of using wormholes as bridges between universes pushes this concept further into the realm of multiverse theories. In many models, our universe is just one bubble within a vast multiverse, comprising countless universes with varying physical constants and laws. If wormholes could connect different bubbles, it would suggest a universe where transportation is possible not just across vast distances, but across entirely separate dimensions of reality. Some solutions, like traversable wormholes, would need to remain open for humans or signals to pass through, and this requires properties that seem to defy known physics. Consequently, while wormholes remain a fascinating theoretical tool, there is no empirical evidence that they could be stabilized or used for inter-universe travel. Experimental efforts to detect natural or artificial wormholes have been limited, mostly because they would be incredibly difficult to observe directly. Some physicists have proposed that phenomena, such as gravitational lensing, where light bends around massive objects, might hint at the presence of wormhole-like structures. If a wormhole were to exist between two universes, one might expect unusual cosmic signatures, like unexplained distortions or signals that do not fit traditional models of space-time curvature. Yet, these signatures could easily be misinterpreted or remain hidden behind the vastness of cosmic noise. As a result, wormholes as gateways between universes are generally regarded as intriguing hypotheses rather than imminent scientific possibilities. From a conceptual standpoint, the idea that wormholes could serve as portals between universes sparks both curiosity and skepticism. The mathematics of general relativity provides elegant solutions, suggesting such shortcuts might exist, but translating these solutions into physical reality raises profound questions about the nature of space-time, stability, and the limitations imposed by quantum mechanics. Some advanced theories, including string theory and quantum gravity, explore the possibility of multi-branch space-time structures, hinting at a universe far more interconnected than we perceive. While practical travel through wormholes remains a distant dream, studying their theoretical foundations pushes the boundaries of our understanding of the cosmos, blurring the line between science and speculative imagination. Evidence and observational challenges in multiverse theories. The concept of traveling to a parallel universe remains firmly within the realm of speculation and theoretical physics, with evidence serving as an elusive goal. Current multiverse models, whether stemming from eternal inflation, string theory landscapes, or quantum mechanics interpretations, suggest that other universes may exist in separate dimensions or regions of space-time, but these are inherently difficult to observe directly. Unlike planets or stars, whose presence can be confirmed through telescopic imaging or electromagnetic signals, these alternate realities are often predicted to be beyond the reach of conventional detection methods. The nature of their separation from our universe means they do not emit light or signals that can be captured or analyzed using current technology. Observational challenges are compounded by the fact that many multiverse theories are fundamentally untestable with typical empirical approaches. For example, in cosmic inflation models, bubble universes might be spatially separated so far that their effects are completely isolated from our observable universe. While some theorists propose that collisions between universes could leave detectable imprints in the cosmic microwave background, CMB, radiation, such signals have yet to be conclusively identified. The difficulty lies in distinguishing genuine multiverse signatures from foreground noise or cosmic variances. Similarly, string theory's landscape suggests a vast string configuration space, but the sheer enormity of possible universes makes it impossible to map or observe them directly. Another obstacle stems from the intrinsic limitations of current physics. Many of these theories rely on energy scales and physical conditions far beyond what can be recreated or observed with existing experimental setups. For instance, testing the existence of extra dimensions, integral to some multiverse models, would require energies vastly exceeding those achievable in particle accelerators. Without direct access, researchers rely heavily on indirect evidence, such as subtle deviations in gravitational behavior or quantum effects, to infer the plausible existence of other universes. Yet, such indirect signs are often ambiguous, leading some scientists to question whether the multiverse is scientifically robust or simply a philosophical extension of theoretical physics. Moreover, the philosophical implications intertwine with the scientific hurdles. If alternative universes are forever hidden behind barriers of cosmic scale or different physical laws, their existence becomes difficult to confirm or falsify. The principle of falsifiability, a cornerstone of scientific inquiry, challenges the status of multiverse hypotheses. What constitutes observable evidence in such a context? Some propose that the only credible signs might come from predictive excess, such as probabilistic distributions of particles or constants in our universe aligning with multiverse-based predictions. But even these are deeply contentious. The crux of the issue remains that we are limited to our local universe, and until new methods or technologies emerge, the traversal or even confirmation of these parallel realities will remain an uncharted, perhaps impossible, endeavor in empirical science. Theoretical frameworks for interuniversal travel. Speculative physics often ventures into the idea that our universe may be just one bubble in a vast multiverse, a collection of countless universes that coexist in some higher dimensional space. Among the theoretical models supporting this view, the concept of cosmic inflation provides a foundation. Inflation theory suggests that if the universe experienced rapid exponential expansion moments after the Big Bang, different regions could have stopped inflating at different times, creating pocket universes with distinct physical laws and constants. These pockets, or bubbles, might be separated by minuscule or even impossible to cross boundaries, but the underlying mathematics lets us imagine scenarios where travel between them could someday be conceivable. Parallel universe hypotheses often draw upon string theory and M theory, which posit that our universe exists on a membrane or brane within higher dimensional space. In these models, what we perceive as gravity and space-time are confined to our brain, but other branes could exist in close proximity. If mechanisms such as brane collisions or quantum tunneling could be harnessed, they might create gateways or bridges, conceptual wormholes, that could connect these separate but adjacent universes. Such bridges are inspired by solutions to Einstein's equations that admit wormhole geometries. However, their stability, traversability, and existence in reality remain purely theoretical at this point. Quantum mechanical principles also entertain the possibility of interuniversal interactions. The many-worlds interpretation of quantum mechanics, for instance, implies that every quantum event branches into a separate universe, effectively creating an infinite tree of parallel realities. Some thinkers speculate that these branches might be interconnected in ways that could, under extraordinary conditions, allow for the transfer of information or even matter between them. While this remains deeply speculative and beyond current technological reach, researchers have explored ideas like quantum tunneling and non-local correlations that could, in theory, facilitate some form of interuniversal communication, if not physical travel. In the end, These frameworks blend the boundaries of what is scientifically rigorous and what sparks the imagination. They serve as intellectual playgrounds, inspiring both physicists and science fiction writers alike. Although concrete pathways to traversing these alternate realities do not currently exist, nor do they have experimental support, advances in understanding the fabric of space-time and quantum phenomena keep the conversation alive. The idea of journeying to a parallel universe pushes the limits of imagination, bridging the gap between abstract mathematics and the fundamental nature of reality. Potential technologies for accessing parallel universes. Quantum mechanics offers some of the most tantalizing hints toward accessing parallel universes, notably through the concept of the multiverse. The many-worlds interpretation, MWI, suggests that every quantum event spawns a branching universe, creating an infinite tapestry of realities. In theory, harnessing this idea might involve manipulating quantum superpositions on a macroscopic scale. For example, experiments with quantum entanglement and decoherence aim to probe the boundaries between our universe and these potential alternate realities. Though still highly speculative, advances in quantum computing and quantum control could someday enable us to observe or even interact with these parallel branches, effectively giving us a window into other universes. Tachyonic particles, hypothetical faster-than-light entities, emerge from some advanced theories in particle physics and could represent a portal-like mechanism. These particles, if they exist, would defy conventional causality, potentially allowing information or matter to travel between different points in space-time, including parallel universes connected through higher dimensions. While direct evidence for tachyons remains elusive, experiments in high-energy physics laboratories continue to seek signatures of such particles. Should tachyons or similar phenomena be confirmed, they might serve as the gateway for actual crossings or communication with alternate realities, making the concept of traveling to other universes more than mere science fiction. Another intriguing avenue involves the manipulation of space-time itself through wormholes, hypothetical tunnels that connect distant regions of space and, theoretically, separate universes. Building on Einstein-Rosen bridges, physicists explore conditions under which these would be stable and navigable. Advanced theories suggest employing exotic matter, material with negative energy density, to keep these wormholes open. While the effort to produce or stabilize such constructs remains far beyond current technological capabilities, the mathematical frameworks are robust enough to inspire ongoing research. If someday we could engineer or locate natural wormholes, they might function as portals, offering a practical method to access parallel realms directly. Finally, the realm of string theory and higher dimensional spaces presents another pathway towards parallel universe exploration. These models propose that our universe is but a membrane, brain, floating within a higher dimensional space, often called the bulk. Interactions between brains, or the possibility of slipping into an adjacent brain, could theoretically be achieved through high-energy particle collisions or gravitational manipulations. Experiments in collider physics, such as those conducted at CERN, attempt to detect signs of extra dimensions, possible evidence that these connections exist. Discovering a way to interact with neighboring brains might open doors to entirely new universes, transforming our understanding of reality from confined to multidimensional. Physical and energetic barriers to travel. Conventional physics provides little support for the notion of traveling between parallel universes, often referred to as multiverses, because such concepts stretch the boundaries of what is considered empirically accessible. The primary obstacle stems from the nature of space-time itself. According to general relativity, the fabric of the universe is curved by mass and energy, and while mathematically multiple solutions exist, none currently offer a feasible pathway or mechanism for crossing into alternate dimensions. Theoretical constructs such as wormholes, which are sometimes invoked as gateways to other universes, introduce their own set of formidable barriers, primarily their stability and the enormous energy required to keep them open. These structures tend to collapse or disconnect long before they can be traversed, making their practical use highly doubtful with our current understanding. On a more energetic level, the barriers to universe hopping become even more abstract, but no less daunting. Quantum theory suggests that if parallel worlds or multiverses do exist, they're separated by what some call an energy barrier, a conceptual boundary in the quantum state space that prevents spontaneous transitions. To breach such a barrier would require an energy input beyond anything we can currently sustain, possibly involving manipulation of exotic states of matter or harnessing energies on the scale of entire cosmic events. No known particle or force appears capable of bridging such extreme energetic divides, and attempting to do so might require technology that operates far outside current physics, perhaps involving manipulation of hypothetical constructs like negative energy densities or higher dimensional spaces. Furthermore, these barriers are not merely physical or energetic, but also deeply rooted in the fabric of reality itself. Many theorists posit that different universes might be separated by dimensions that are simply inaccessible due to incompatible physical constants or fundamental differences in how physical laws apply. This could mean that even if one could devise a method to overcome energetic thresholds, the underlying properties of alternate universes, such as laws of thermodynamics, particle interactions, or the structure of spacetime, may prohibit any meaningful or stable form of travel. The metaphysical implication is profound. What might seem like a technical challenge could be an innate feature of the multiverse architecture, rendering these journeys impossible in principle, not just in practice. In summary, the obstacles to traveling to a parallel universe are a complex network of physical, energetic, and fundamental barriers. Current scientific understanding suggests that such travel, if it is indeed possible at all, remains infinitely remote, reachable only through advances in physics that may forever be beyond our grasp. Whether these barriers are insurmountable by nature or simply by our present knowledge is a question that continues to inspire both scientific inquiry and imaginative speculation. Causality, paradoxes, and the nature of reality. The concept of traveling to a parallel universe challenges our understanding of causality, the fundamental relationship between cause and effect that underpins all of physics. In our everyday experience, causes precede effects in a consistent, logical order, but in the realm of multiverse theories, this relationship becomes more complex. The many-worlds interpretation of quantum mechanics suggests that every quantum event spawns a branching universe, creating an infinite web of alternative realities where every possible outcome occurs simultaneously. If one could somehow navigate these branching pathways, the idea of cause and effect might break down or become nonlinear. This raises questions about whether actions in one universe could influence another or violate the principle that events in the past determine the future. Paradoxes often arise when considering the possibility of traveling between these universes. The classic grandfather paradox applies here. If a traveler goes back in time in an alternate universe and prevents their grandparents from meeting, that traveler would never have been born. But within the multiverse framework, this scenario might not involve altering one's original timeline, but creating an entirely new branch where the grandparent never married. Nevertheless, this leads to its own set of philosophical issues. If every action creates diverging realities, then the notion of change or causality within a single timeline becomes fuzzy. Can a universe maintain consistent physical laws if multiple versions of reality are continually splitting? The paradoxes serve as fertile ground for imagination, but also highlight the unresolved tensions between quantum mechanics, relativity, and our intuitive grasp of reality. The nature of reality itself is called into question by these ideas. If reality consists of an ever-expanding multitude of parallel universes, what does that say about the uniqueness and stability of the universe we experience daily? Is our universe merely one bubble among countless others, each with its own distinct physical constants and laws? Theoretical physicists debate whether these parallel worlds are entirely separate entities with no interaction or if some form of subtle crossover could allow for information transfer or influence. Some quantum theories propose that reality is a vast, interconnected multiverse fabric, where causality pervades, but in a far more intricate, multidimensional way than simple linear cause and effect. The prospect of traveling, either physically or through consciousness, remains speculative, but contemplating it forces us to reconsider the very fabric of existence and the boundaries of reality. Philosophical and ethical implications of multiverse travel. The prospect of traveling between parallel universes raises profound questions about identity and moral responsibility. If a multiverse exists, and we find means to access alternate realities, are the versions of ourselves in those worlds truly the same person? Or do they embody different choices and circumstances, effectively creating new entities with their own rights and consequences? This suggests a complex tapestry where every decision spawns a new branch of reality. Ethical considerations then extend beyond mere curiosity. Does intervening in these other worlds impose a moral obligation to avoid harm? If so, our actions in one universe could ripple across countless others, raising issues akin to those discussed in philosophy of the mind and personal identity. From a utilitarian perspective, the possibility of multiverse travel introduces dilemmas about maximizing well-being while minimizing suffering. If we could explore a universe with less suffering, perhaps eradicating disease or poverty there, would we have the duty to do so? Conversely, some theories posit that our interference might lead to unintended consequences, creating chaotic ripples across the multiverse. This echoes the butterfly effect in chaos theory, but on a cosmic scale, making the ethics of intervention more tangled. The potential for exploitation also lurks. Consider the idea of harvesting resources from alternative worlds or treating their inhabitants as commodities. Such actions challenge deeply ingrained notions of morality and respect for other sentient beings, even if those beings are in alternate realities. Philosophically, the concept of multiverse travel compels us to rethink notions of reality, agency, and moral agency. If multiple versions of ourselves exist, each with their own free will, what does that say about personal responsibility? Is accountability diminished because decisions are replicated across countless realities? Or is it amplified, knowing that every choice might spawn a new universe? Ethical frameworks may need to evolve, incorporating a multiversal perspective that balances the value of autonomy in each universe against the interconnectedness implied by possible travel. These considerations challenge the very foundations of moral philosophy, pushing us to confront questions about the nature of suffering and happiness across multiple dimensions. Finally, the ethical landscape of multiverse exploration inevitably raises concerns about societal inequality and justice. If access is limited, say, only available to those with immense technological power or wealth, such disparities could exacerbate existing social divisions, creating a universe where some live in vastly better conditions than others across countless realities. This inequality could be justified or condemned, based on the premise that manipulating or traversing multiverses might perpetuate or even amplify systemic inequalities. The philosophical debate includes whether such actions could be deemed ethically permissible if the benefits are immense, or whether it fundamentally violates principles of fairness. As our understanding of multiverse theories continues to develop, these questions remain central to the ongoing conversation about humanity's right or duty to explore realities beyond our own. The future of multiverse research and speculative travel. The quest to understand the multiverse hinges on cutting-edge physics, particularly the theories of cosmic inflation and string theory, which propose the existence of multiple, perhaps infinite, universes. Cosmic inflation suggests that shortly after the Big Bang, different regions of space experienced varying rates of expansion, creating bubble universes that are causally disconnected from our own. Meanwhile, string theory posits a multiverse composed of vast membranes, brains, that ripple through higher dimensional space, each representing a separate universe with its own physical laws. While these ideas are compelling in their mathematical rigor, direct observational evidence remains elusive. Researchers continue to analyze phenomena, such as the cosmic microwave background for subtle clues, imprints of interactions with other universes, perhaps through collision events or quantum fluctuations. These investigations balance on the frontier of empirical science, flirting with the limits of what experiments can currently achieve. Looking toward the horizon of multiverse research, technological innovations might push us closer to seeing between these cosmic realms. Quantum computing, for instance, offers a promising avenue by simulating conditions that could mirror multiverse interactions, allowing scientists to test hypotheses in high-fidelity virtual environments. The development of ultra-sensitive detectors, capable of capturing faint gravitational waves or signals emanating from multiversal boundary conditions, could further expand our observational toolkit. Although the idea of physically traveling to another universe stretches beyond our current grasp, these indirect methods could someday provide enough evidence to validate or falsify the multiverse hypothesis. Theoretical physicists are also debating whether wormholes or quantum tunneling mechanisms, long considered speculative, might serve as gateways, albeit on scales and energy levels that seem far beyond accessible technology. Speculation about traveling between universes has increasingly intertwined with science fiction and theoretical physics. While actual crossing remains a distant dream, some proposed models suggest that if wormholes could be stabilized and enlarged, perhaps through exotic matter with negative energy density, then, in principle, a form of transit might be conceivable. Such scenarios often dwell within a realm of advanced quantum gravity theories, where space-time itself could be manipulated or folded like paper, creating shortcuts through higher dimensions. Even if these notions are purely hypothetical for now, the possibility fuels both scientific inquiry and philosophical debate about the nature of reality. The future may see carefully designed thought experiments and experimental analogs that could clarify whether multiversal travel is more than an imaginative leap or a profound misconception. As our understanding deepens, the line between scientific theory and science fiction will continue to blur. Future breakthroughs might not immediately allow actual travel, but could instead revolutionize our grasp of reality's fabric, perhaps revealing that the multiverse is more accessible than it seems, or that it influences our universe in ways we have yet to comprehend fully. The journey into multiverse research is ongoing, driven by curiosity and the relentless pursuit of knowledge. Whether or not we will someday step beyond our own universe, the exploration pushes the boundaries of human imagination and science, offering glimpses into a cosmos far richer and more layered than we can currently fathom. The notion of traveling to a parallel universe touches on both the limits of modern physics and the boundless realm of imagination. Current scientific understanding suggests that our universe is just one of potentially an infinite number of universes, collectively known as the multiverse. The concept finds its roots in various theories, such as quantum mechanics, string theory, and cosmology. For example, the many-worlds interpretation of quantum mechanics posits that every quantum event spawns a new universe, creating a branching hierarchy of realities. This means that, theoretically, every possible outcome of every event exists somewhere in this vast multiverse, including worlds where history took different turns or physical laws differ subtly or significantly from our own. Despite these intriguing ideas, the practical aspect of travel remains highly speculative. We currently lack the technological means or even a comprehensive understanding of how to access or navigate these other realities. The concept of wormholes, hypothetical bridges in space-time, has frequently been discussed as a potential pathway between universes. Wormholes are solutions to Einstein's field equations, but whether they can exist or be stabilized for safe travel is still debated among physicists. Nonetheless, the idea remains seductive. If wormholes or other exotic phenomena could be harnessed, then perhaps interuniversal travel might one day be within the realm of possibility, akin to stepping through a portal rather than merely jumping through space. The challenge extends beyond pure physics into philosophical and metaphysical questions. Would traveling to a parallel universe alter one's identity or sense of self? If two selves diverged through different life choices, would crossing into a universe where your alternate self exists evoke ethical dilemmas? These questions underscore that even if the physics enables access, the consequences of such journeys are far from fully understood. Moreover, the immense energies and precise conditions required to manipulate space-time at such scale suggest that, for now, traveling to other realities remains an elusive dream, more a question of future science than of current technology. Still, ongoing research continues to blur the line where science ends and imagination begins, expanding our ideas about the fundamental nature of reality itself. While the notion of traveling to a parallel universe remains within the realm of speculative physics and the boundaries of our current technological capabilities, exploring these ideas sparks our curiosity and challenges our understanding of reality itself. We examined what theories like the multiverse hypothesis and quantum mechanics suggest about the existence of alternate worlds, and how concepts such as wormholes and cosmic inflation might one day open doors to these distant realms, if they exist at all. For now, the questions continue to push the limits of scientific inquiry, reminding us that the universe, or multiverse, is far more mysterious than it appears. To all our curious thinkers and dreamers, keep pondering these frontiers. Each discovery fuels the imagination and drives future breakthroughs. Stay tuned for more explorations into the cosmos and the mind-bending possibilities that lie beyond what we see today. If your curiosity is as boundless as the universe itself, don't forget to like, share, and subscribe. There's so much more to uncover together. Until next time, keep questioning and keep dreaming.